All right, it is with distinct pride that we welcome this week Josh Bendavid, one of our own. He was here at Caltech as a fellow 2015 to 17. Josh did his undergraduate in Canada. He worked with William Trischuk. He was at the Atlas collaboration at the LHC. And he did a lot of work there, but then we got him at CMS and he never left. He went to do his PhD at MIT with Christoph Paus. His PhD title was Search for a Narrow Resonance in the Diphoton Channel. By the time that he gave it to the committee, it became evidence for. This thesis was the discovery of the Higgs in the Diphoton Channel. So you have somebody who actually did the discovery. For that, he has been, of course, the expectations of Josh have been ever since increasing. And in the past 7 years, he has been working on the W mass measurement. I should say after MIT, he was a fellow at the CERN. He was a fellow here. He became the equivalent of assistant professor at CERN. And bounced between CERN and the US at MIT, where he is affiliated still now as a research scientist. And as of this week, he was offered the CERN permanent position physicist. So it is, and he found out on the way from CERN to here. So this is an incredible path, a career path. And not only he will talk to us about precision and discovery path in particle physics, but he has started working already for the physics of the FCC, together with the experimentalists, the theorists, and all the people from all the various institutes in the US and elsewhere at CERN. So with that, Josh, thank you for being here.
Well, thank you very much, Maria, for the introduction. Okay, so I'm going to talk today about a little bit of recent history, some of the things which are going on at the LHC today, and some perspectives for the future direction of collider physics. So, of course, the standard model of particle physics describes all of known physics except for gravity, dark matter, dark energy, the baryon asymmetry, neutrino oscillations, the microscopic nature of spacetime, and maybe one or two other things. It's a relativistic quantum field theory of fermions and gauge bosons, which describes the strong and electroweak interactions. But of course, with this alone, the theory would predict massless fermions and bosons, which of course we know empirically is not the case. And so the solution to this is the Higgs mechanism, in which the symmetry of the vacuum is spontaneously broken, leading to a ground state where the Higgs appears as a massive scalar field. And the other 3 degrees of freedom become the longitudinal polarizations of the W plus, W minus, and Z bosons, giving them mass. And the coupling of this Higgs field with the fermions leads to the fermion mass terms. And you'll see how that actually plays out in the experimental observations at the LHC in order to really demonstrate that this is the case, that this really is the origin of the fermion masses in the universe. The LHC is a proton-proton collider. It's 27 kilometers in circumference. It's located at CERN in the Geneva region. The design energy was 14 TeV. It's currently operating at 13.6 TeV, so just about there. The sort of backbone of the machine are the superconducting dipole magnets with a design field of 8.3 Tesla, and they're cooled to 1.9 Kelvin using superfluidic helium, which is, of course, an enormous engineering feat to maintain that around the entire 27-kilometer ring. There are 1,232 dipole magnets, and of course, every single one of them and all of the other components in between have to be operating in order for the accelerator to run. Despite that, we manage really, some spectacular uptimes, even in excess of 60% these days during the running periods of the LHC. This is the CMS detector. There's also the Atlas detector, which is somewhat different, but similar in concept in the sense that it's a sort of 4 pi detector, which is built around the interaction point where the particles collide, and you have all of the different subdetector components which measure the momentum and energy and contribute to the identification of the different types of particles. There are a number of different stable, quote unquote, particles that can be produced in the collisions. Of course, when we say stable particles, from our perspective, we're talking about ones which, traveling near the speed of light, don't decay in the sort of 10-meter length scales of our detector. So muons, of course, will eventually decay, and so will charged pions, but not within the length scale of our detector, given the prevailing energies. And what we do is that we sort of correlate the signals between the different subdetectors, and we use that in order to determine which type of particles we're looking at as we measure their momentum and/or energy. So the muons go all the way through the full detector. Electromagnetic particles deposit their energy in the first layers of the calorimeter. Charged hadrons in the second layer. Charged particles leave ionization deposits in the silicon detectors, and so on and so forth. This is a sort of overall summary, if you like, of the CMS physics program. And of course, it's very small, but what this is showing is this is actually showing measured collision cross sections over 14 orders of magnitude, all the way from this sort of inclusive inelastic collision cross section for the protons down to processes which are 1 in 1,000 trillion sort of probabilities. And of course, we're able to access such rare processes at the LHC because we really do have trillions and trillions of collisions. In the current operating conditions of the LHC, while the machine is running, there are about 1 billion proton-proton collisions per second while we're running the machine. And of course, we only ultimately record a small fraction of those because most of them are these inelastic collisions, which are relatively less interesting by now, so that we can focus on some of the rarer processes. You can see a similar plot from Atlas, where you can see, in this case, the cross-section on the y-axis, and here you can see more clearly from 10 to the 11 picobarns down to 10 to the -3 picobarns, so 14 orders of magnitude, and all of the processes that are measured, each of them compared, by the way, to a theoretical prediction based on perturbative QCD. And so this whole program that you can see as a snapshot here is really a spectacular confirmation of the standard model and of perturbative QCD and of our understanding of how we do the calculations, how we match perturbative QCD to the proton structure, et cetera, et cetera. And there's really a huge range of things that we can measure, including access to the Higgs for the first time and across a range of production modes. Of course, an important part of the LHC program has also been direct searches for physics beyond the standard model. And this is a summary of searches for supersymmetry at the LHC, given in terms of different final states and in terms of the mass scale. And so what you can see is that there have been really a wide range of searches carried out across a very comprehensive set of final states that cover a mass scale up to between 1 and a few TeV. And of course, unfortunately, we haven't seen any evidence of new physics in these direct searches so far. But it does mean that a pretty wide range of parameter space is actually ruled out by the full search program at the LHC. Now, of course, in 2012, after the first few years of operations of the LHC, we discovered the Higgs. And this is the cover of the journal edition in which the discovery paper appeared with the selected plots from CMS and from Atlas. The magnifying glass was, I must say, the addition of the journal editors, but the plot otherwise comes from my PhD thesis. So this was, of course, a very nice moment for me. And here you can see the spokesperson at the time, Joan Candela of CMS, Fabiola Gianotti of Atlas, who's, of course, currently the CERN Director General, and Rolf Heuer, who was the Director General of CERN at the time. And, the auditorium was full and the media waiting outside then for the press event, and it was a very exciting time, obviously. Now, the Higgs can be produced and decay in quite a number of different ways at the LHC. But there were two channels in particular that played a special role in the search for and the discovery of the Higgs at the LHC. So one of them is Higgs decaying to two Z bosons, which then decays to 4 leptons. And the reason for that is that the processes which produce charged leptons at the LHC are relatively rare because they have to proceed through weak interactions, which are, of course, much less likely than the strong interaction. And so to have 4 of them is really an extraordinarily clean final state. Now, the trade-off is that you pay in the branching fractions, and so it's a very small fraction of Higgs events that actually decay in this way, but it's very clean, as you'll see from the plots, which I'll show you in a moment. And then instead, as a sort of compromise, you have Higgs to photons, which has a relatively larger branching fraction, but one must contend with larger backgrounds from other standard model processes. Now, the special features of these two final states is that it is possible to fully reconstruct the final state in the sense that there are no neutrinos. And so that means that the full mass and energy of the Higgs can be completely reconstructed in those events. But also in our detectors, the electrons, muons, and photons are relatively well reconstructed objects with very good energy or momentum resolution. In particular, this involves only the tracking detectors or the electromagnetic calorimeters and is not subject to the relatively larger fluctuations which occur in hadronic showers, which makes them more difficult to measure with good energy resolution. And so for the same reason, these channels ultimately play a special role as well in the measurement of the Higgs mass and in the measurements of Higgs differential cross-sections, where we actually really know the kinematics of the Higgs very precisely in each of the events in which it is reconstructed. You can see here the snapshot of what these distributions looked like at the time of the discovery. So this was including 5 inverse femtobarns of data from 2011. So this was the 7 TeV run, and then the first 5 inverse femtobarns of data from the 8 TeV run in 2012. And so these were the plots which were shown on July 4th. And so you can see here the 4 lepton mass distribution from CMS. And you can see the expectation for the Higgs peak here, and you can see that, well, there's 4, 5, 2 events, so really only a handful of events in the peak, but nevertheless quite statistically significant with respect to the background expectation. And you can see also in this distribution this sort of self-calibrating nature, in that we have the by this point already known Z boson, which normally would decay to 2 leptons, but actually does have some smaller probability to decay to 4 leptons. And so you can see also the peak here around 90 GeV. And you can see the similar plot from Atlas with the Higgs as the small peak here in blue. The 2 experiments are, of course, very complementary, and it was a critical aspect of the entire program to have the confirmation of the discovery between the 2 experiments. But alas, we were never able to agree on the color scheme for the different processes, and that persists to this day across a range of measurements and plots. If you fast forward, so this is what the corresponding plots look like using the full LHC Run 2 data. So this is the data which was collected up to the end of 2018. And you can see that, we went from 10 inverse femtobarns here to 137 inverse femtobarns. And now you can see that there are hundreds of events in the peak. And one doesn't discuss anymore the statistical significance because, well, it's quite obvious that it's there. And we've long since moved on instead to sort of precise measurements of its coupling and its properties and all of the other things that we can do with this fantastic data. You can see similar plots that were shown at the time of the discovery in the diphoton channel. And so here you can see that you have this sort of much larger background from standard model processes. So this is sort of this smoothly falling continuum spectrum, mostly from other standard model processes which produce 2 photons. But you can see here this small but clearly visible peak at the well-defined mass of the Higgs with hundreds of events in it. Now, these plots are sort of summarizing something which is somewhat more complicated going on underneath, where there are actually sort of 5 or 10 or 20 different mass distributions that go in, which are sort of categorized according to signal to background, according to the expected energy resolution of the photons, et cetera, using machine learning techniques in a thoughtful way in order to, on the one hand, enhance the sensitivity, but on the other hand, maintain the sort of basic feature of this search as a bump hunt for a narrow peak on top of a smoothly falling background. And this is what it looked like at the time of the discovery. And then, of course, again, if you go to 140 inverse femtobarns up to the end of 2018, then you can see, well, there's way more events. And again, a very clear peak. The statistical fluctuations are heavily suppressed as we add more data. And we have, again, long since moved into relatively precise measurements of the cross sections of the mass of the couplings of the properties. And so in that respect, you can see here, so on the left is showing the rate of Higgs events produced and then decaying in different modes. You can see the two photons, the two Zs, the two Ws, the two taus, Bs, muons, Z gamma, with different precision depending on the relative number of events which are produced and the relative difficulty of measuring them. You can see that they all agree with the standard model expectation within the uncertainties. And I said at the beginning that in the standard model, the mass of the fermions comes from the Yukawa coupling of the Higgs to the fermions. And so if that's true, then the relationship between the mass of the particle in terms of its rest energy and the strength of its coupling to the Higgs as measured through these production and decay cross sections should be linear. And indeed, if you plot it in this way, what you find is across the full range of masses that we're able to access in this context, from the muons all the way up to the top quark, this relationship holds and is consistent. And so this plot is a sort of spectacular confirmation of this fundamental feature of the standard model, that the masses of the fermions come from the coupling to the Higgs. Of course, we would also like to measure this for some of the lighter quarks and the electrons, but this is very difficult because the coupling of the Higgs to those particles is so weak, and because their masses are small. And that is one of the things for which we will need to rely on future colliders. And so after the Higgs was discovered, relatively quickly, its mass was measured pretty precisely, sort of at the per mil level. And so the discovery of the Higgs completes the particle content, if you like, of the standard model. This is the last particle which is predicted to exist in the standard model, which had not yet been observed up to 2012. And the precise measurement of its mass provides the inputs. It's the last sort of free parameter in the standard model. And what that means is that for the first time, we had the complete set of inputs needed to over-constrain the standard model. Now, the standard model has quite a large number of free parameters, and the precise value of them is not predicted a priori, but the relationships between them are predicted. And so there's a very well-defined relationship, for example, between the mass of the W boson, the mass of the Z boson, and the weak mixing angle, which is related to the precise manner in which the symmetry of the electroweak vacuum is broken. And so if you measure two of those, plus the other parameters to take into account the additional virtual corrections, you can predict the third. And so you can see here, for example, in the plane of the weak mixing angle on the x-axis and the W mass on the y-axis, you can see the theoretical prediction in blue compared to the experimental measurements up to 2018 in this plot in green. And by comparing these things, it acts as a sort of internal consistency test of the standard model. And if the experimental measurements don't agree with the indirect predictions from the standard model, then it could imply, for example, the presence of new particles or new interactions which modify these virtual corrections and lead to a different result. And so in this way, precision measurements of the standard model parameters are indirectly searches for new physics, and potentially searches for new physics with a reach in terms of energy scale, which is much greater than what can be directly accessed from searches for new particles produced in the collisions. Now, one of the interesting things here is that as the LHC precision physics program took off in earnest, it was realized that actually for many of these measurements, the LHC experiments could be competitive or even in some cases surpass the precision which was achieved at LEP an electron-positron collider where you know, the environment is much cleaner and is in principle much better suited for doing these types of measurements. But the luminosity of the LHC and the production cross sections for W and Z bosons is so high that we have enough of them that we start to be able to make really competitive measurements. So this plot is showing the weak mixing angle of the electroweak symmetry breaking measured by CMS, in this case from the forward-backward asymmetry of Z bosons, which is related to the relative strength of the coupling of Z bosons to left-handed versus right-handed fermions, and compared to the corresponding measurements from LEP and SLD. And what you can see is that it's sort of the same ballpark. It's competitive. It's not quite surpassing the precision yet, but it sure is getting there. One of the ways that we're able to do that is that one of the big uncertainties that could limit the precision of these sorts of measurements at the LHC is the fact that when you collide protons, the actual interactions that we're interested in are actually the interactions between the quarks and gluons inside the proton. And so there's a significant uncertainty from the fact that we have a limited knowledge of the energy distribution of quarks and gluons within the proton. And of course, that can't be calculated very precisely from first principles because because QCD becomes non-perturbative in those energy ranges at the confinement scale of the proton mass. And so that's quite difficult, and we rely on empirical models that are then measured from a range of other data. But we can play a trick here, which is that the data that we use, which is sensitive to, in this case, the weak mixing angle, is also in its own way, but differently, sensitive to the distribution of quarks and gluons within the proton. And so we can make a simultaneous measurement of the quantity we're interested in, the weak mixing angle in this case, and the energy distribution of the quarks within the proton. And so in this way, we go from the blue line in terms of uncertainty down to the red line. This is sort of a factor of 2 since this is on a logarithmic scale. But more importantly, if we do a projection to what we expect from, let's say, the full LHC, high luminosity LHC data set through the end of the 2030s, you can see that if we were not able to do these in situ constraints in parallel to the actual measurement of the parameter of interest, we would saturate. We wouldn't gain in precision as we add more data. And instead, by doing this sort of parallel simultaneous determination, we're able to get back to this red curve where the uncertainty is still decreasing as we increase the amount of data. And so in this way, even just by this means, by adding more data, we do expect to be able to reduce the uncertainty on this particular quantity by at least another factor of 2. And of course, we have other means by which to do this potentially even better. You can see also as another example, tests of lepton universality. So this is a measurement from ATLAS, which is testing the universality of the coupling of the W boson to muons, the second generation charged lepton, versus taus, the third generation charged lepton. This quantity should be just about 1 in the standard model. And you can see that there was historically a sort of small 2 sigma level tension from the LEP measurement. And you can see that the measurement from ATLAS at the LHC actually has much better precision on the one hand and actually agrees with the standard model on the other hand. Likewise, you can see here from CMS a result for the anomalous magnetic moment of tau leptons. So you may have heard of the muon G-2 measurement, the anomalous muon magnetic moment measurement at Fermilab in a dedicated experiment. Here, we're actually able to access the similar quantity for third generation leptons. Of course, not at the same level of precision, but in case that there was beyond standard model physics, which behave differently with respect to the third generation, we would be sensitive to it. Alas, the measured value is fully consistent with the standard model, but actually much more precise than any of the previous measurements, even the ones from the much cleaner environment at LEP and electron-positron collider. And then finally, most recently, the measurement of the W boson mass from CMS, where you can see here the distribution after the statistical interpretation, where we're really talking about control over the expected number of events at the level of per mil for this distribution with sort of order 100 million W candidates. And we achieve an uncertainty of 9.9 MeV, which is the most precise measurement at the LHC and comparable in precision to the recent CDF measurement, which was quite discrepant with the standard model expectation. This most recent measurement instead agrees with the standard model expectation and with the other measurements, but is in clear tension with the CDF one. Probably this goes substantially in the direction of putting this discrepancy to rest, but we'll see how this evolves in the future. And actually, we have quite some means to improve the precision of this measurement through more data, through additionally improved analysis techniques, et cetera, as we go forward. And probably here also another factor of 2 in precision is achievable at the LHC, even using the data that we've already collected up to this point. Now, I want to just divert a little bit and talk about some technical aspects. So these high precision measurements at the LHC require large data sets on the one hand. You saw here a plot that has some order 100 million events, but also accurate modeling of systematic uncertainties. And so a fast turnaround time is actually critical as the physicist waits, because we need to be able to do development of the analysis and iterate and add new models for systematic uncertainties, test different models for systematic uncertainties, et cetera, et cetera. And if it takes a month to chew over the data, then it really limits what we can do, because it means that the number of things that we can test, if it takes us 5 years to do the measurement and it takes a month to chew over the data, there's only about 50 different things that we can test. And that's not enough. There's much more going on. There's many more things that need to be tested. And so we really need to be able to do this quickly, flexibly, and reliably. And so here's just one particular technical example. So this is a very basic analysis operation of filling the events into histograms. It's sort of a core technical function that needs to be done in order to do this type of measurement. This particular example leverages, let's say, mega threading, so multi-threading, but with hundreds of threads on modern servers, and intelligent handling of the data to achieve 100-fold speed up, going from an hour in this particular test down to 90 seconds, and a corresponding sort of 50 to 100-fold reduction in the memory footprint just from optimizing how we fill the histograms. And so, Moore's law, in a sense, is slowing down as we approach the sort of angstrom scale for the transistors. But there's clever things that we can do, leveraging, evolving computing designs and architectures, and evolving software algorithms and architectures in order to sort of continue improving things and be able to continue scaling up the complexity and precision of measurements at this scale. And similarly, for the likelihood fit, which is used to do the final statistical analysis, we also get a 100-fold improvement using numerical frameworks like TensorFlow, which are typically used for machine learning applications, but they also have the advantage of high-performance, numerically stable gradients and can exploit either a large number of CPU cores or GPUs. And so taking these two things, but also many others into consideration, the full high-level stage of the CMS-NW measurement that I showed you before takes an hour and a half, despite running over 4 billion simulated collision events and about 1 billion actual collision events from the LHC. And the final likelihood fit with 3,000 bins in the templates and some 5,000 nuisance parameters takes less than 1 minute. And this has really been a critical aspect to being able to actually develop and perform and do all of the necessary cross-checks for a measurement at this level of complexity. And of course, as we accumulate even more data at the LHC or at future colliders, these aspects become more and more critical in order to actually be able to do the physics that we want to do. So what's next? Well, there is a very well-developed by now proposal for a new 90-kilometer circular collider at CERN. So you can see here a map of the schematically of the Geneva region. You can see this is the LHC and this is the FCC. So the current name for this project is the Future Circular Collider. Of course, if we get to the point where it's approved and built, we'll have to change the name because you can't call it the Future Circular Collider if it's something which is actually operating. And this would be a 90-kilometer tunnel in the Geneva region. It would actually go under the lake for a few kilometers, around the backside of one of the smaller mountain ranges. It's really the next step in terms of large collider projects. This would come in two stages. There would be the FCCEE, an electron-positron collider, which would act as a Higgs factory on the one hand, to make even more precise measurements of the Higgs properties and to access some of those couplings that we're not able to yet at the LHC, as I alluded to before, but also ultra high precision electroweak measurements, even surpassing what's possible, as impressive as it is, at the LHC. And then the second stage, FCCHH, a 100 TeV scale proton-proton collider, as a next generation discovery machine, but also there actually is one thing which I glossed over. So the discovery of the Higgs completes the particle content of the standard model, but there actually are a few interactions which we haven't directly observed yet, which are related to the Higgs self-coupling, the Higgs coupling to itself, which is of course key to understanding the nature and shape of the Higgs potential. And that's something which we will need very likely this high energy proton-proton collider in order to have a sufficiently precise access to. Now, you can see the sort of timescales that are involved here, and the construction operation of the tunnel, one accelerator, the next accelerator is really a long-term program. So we talk about construction through the 2020s, 30s, first part of the 2040s, operation of this first accelerator between 2045 and 2060, and then operation of the second accelerator between 2065 and 2070, and 2090 or just about to the end of the century. So this is really a very long-term project, but it's at a sufficient scale that the planning needs to start now, and there's a staged construction and physics exploitation in order to get to the end. If we focus on the FCCEE, so that at least, it's a time scale where I'll be, alive, maybe not quite retired, by the end of it, certainly yes. There's quite a lot of physics that can be done here. So first of all, you can see here the luminosity versus center of mass energy, and you can see the different discrete points at which FCCEE was designed to run, each for a different physics purpose. It can run at the Z pole in order to do ultra precise measurements of the Z mass, the weak mixing angle, and a number of other key electroweak parameters, but also flavor physics, as I'll describe in a moment. It can run at the WW production threshold in order to provide another order of magnitude or even better precision on the mass of the W boson, among other things, but also tests of lepton universality and things of that nature. It can run at the ZH production threshold, the energy which was just barely missed by the first LEP collider, in order to fulfill its sort of primary purpose as a Higgs factory and produce a large number of Higgs bosons in a controlled environment in which we can make very precise measurements of its properties. And then finally, it can run at the TT bar production threshold, which would allow us to measure the mass of the top quark, the heaviest particle in the standard model and the heaviest known elementary particle overall, to very high precision and free of the hadronic effects that limit the precision of this measurement at hadron colliders because of nasty effects like color reconnection and the like. And you can see, compared to alternative proposals for a linear Higgs factory, that there's a huge advantage in luminosity at all energies, partly because it's easier to run a circular collider in general at higher integrated luminosity because of less stringent constraints on alignment of the beams and accelerator components and things of that nature, but also because in a circular collider, one can have multiple interaction points. And so this particular plot is made assuming for experiments the same number that we have at the LHC. You can see here a sort of summary of the precision which is achievable in some of these parameters at the Higgs factory compared to the LHC program. And so this is really the path to ultimate precision on the Higgs coupling and properties. And you can see that some of the biggest differences occur for the coupling to these lighter particles. So in this case, to charm quarks, one of the second generation, which is quite challenging at the LHC. It's challenging at FCC as well, but much more feasible. And so, as I said, with this sort of varied and sort of progressive running plan, there's a rich and varied physics program in addition to the core precision Higgs measurements over a range of energies. And so you can see here the sort of numbers that you get in n years of running. So this is like a 15-year running program. You get millions of Higgs events, millions of TT bar pairs, hundreds of millions of WW pairs, trillions of Z bosons. So at the Z pole, the entire LEP1 equivalent data set is collected every minute while we're running the machine in this mode of operation. Now, actually, 20% of Zs decay to B quarks. So if we have 5 trillion Zs, we have 1 trillion BB bar pairs, which are produced in a very controlled environment and at high energies, and which we can measure cleanly with these very nice detector concepts. And so FCCEE is also a B factory and can do precision flavor physics. If you look at the precision electroweak measurements, this really gives orders of magnitude improvement in some of these quantities compared to current experiments, even with the impressive progress that we've made at the LHC. And so we can really talk about measuring the Z mass to 100 keV, measuring the W mass to 500 keV. And so if you take the plot I showed before of the recent CMS measurement and you zoom in, if you take at face value the current central values of the standard model prediction on the one hand and the measurement on the other, then that would actually correspond to a 35 standard deviation tension, which would be clear evidence of new physics. And now, of course, it remains to be seen that as the uncertainties shrink, whether they will actually come out, whether the values will actually come out like this, or if they come out on top of each other, in which case what it means is that we've tested the standard model to a precision 100 times more stringent than we were able to so far, and therefore excluded the presence of indirect effects up to really very high energies. And so this is really a spectacular realization of the physics program that we hope to get over the coming decades. A closer look at the timeline. So the current stage of this project is at the level of the feasibility study, and this could be, a decision or approval of the first stage could be taken by the CERN Council potentially by the end of 2027 or the beginning of 2028. And then, of course, there's a period of construction interleaved with the continued operation of the LHC in its upgraded form, which is currently scheduled to end in 2041, and then beginning the operation of the next accelerator. And so in this way, although the timescales are long, the actual gap between the final operation of the LHC and the initial operation of the new accelerator is actually not so long. And there's lots of interesting physics that can still be done in the last part of the LHC program, where actually the beam intensity will be increased by another factor of 5 or so, and we will have quite a lot more data, both for precision measurements and for direct searches. You can see here a sort of more fine-grained timeline of the current part of the program in terms of finishing the feasibility study, submitting it for the European strategy process, et cetera, towards a possible decision by the CERN member states and the Council. And yet another view of it here in terms of the different stages of feasibility study, pre-technical design report, the beginning of construction, et cetera, with some of the technical, environmental consultation, et cetera, steps mixed in. Of course, it's an expensive project. The construction cost up to the operation at the Z Higgs threshold of about 15 billion CHF, a little bit more to get up to the TT bar threshold. But of course, the cost is spread over quite many years, and about half can be covered by the existing CERN budget. And then for the rest, this is under discussion with the member states, with the United States, with private donors, et cetera, to get to hopefully a positive decision from CERN and from the member states. There are already relatively well-developed detector concepts, both detector concepts that have been developed directly as part of the FCC proposal, but also leveraging detector concepts which have been developed in previous years for ILC or other linear collider proposals. With up to 4 detectors possible, we have the ability to have a sort of range of different strategies and detector technologies and approaches, both to leverage different strengths for different physics topics, but also as redundancy and contingency in case one concept proves more or less difficult. One of the detector concepts that I'm personally very interested in is building on something which is being done already for one of the upgraded LHC detectors, where for the inner silicon detector, we can fabricate wafer scale monolithic chips that have both the readout electronics and the sensors on the same silicon wafer. And so then you don't need a PCB, you don't need bonding, you don't need anything, and you can make them thin enough that you can bend them. And so, you know, we look at our detectors as cylinders, but our current detectors at least are actually a facsimile of a cylinder, because we have these sort of small rectangular elements that are arranged in a cylindrical-like fashion. These sensors can actually be bent into cylinders. And we can have, for the first time, a really cylindrical detector, which, of course, as you go close enough to the beam, this sort of even spacing gives a much more uniform acceptance with a smaller systematic uncertainty, more precision, et cetera, et cetera. But there are quite a number of very interesting and very novel detector concepts building on everything that we've learned up to this point in order to maximally exploit the physics of this detector. There's already quite strong cooperation foreseen with the United States, where it is very much the expectation that if this project is approved at CERN, the United States will participate in a similar fashion at a similar sort of funding fraction as it was the case for the LHC, which is, of course, a substantial contribution in kind for the accelerator, for the detectors, and with physicists and engineering expertise and universities participating. And in addition to that, there's also the discussion and beginnings of R&D work towards a possible muon collider. So this is actually very interesting in the sense that muons are at the sweet spot in mass for a circular collider, because if you build an electron-positron collider, the beam energy is limited by the synchrotron radiation as they go around. And so in a given radius ring, if you make them faster and faster, eventually they're radiating off as much energy as you're putting in. Instead, for a proton collider, you're limited by the strength of the dipole magnets that are needed to keep the protons along their circular path. And so the muons are sort of perfectly in the middle. They don't radiate anywhere near as much as the electrons, and they don't need nearly as powerful magnets to keep them in the circle, with the minor detail that they're unstable. And so it's a major challenge to produce, cool them into beams, and accelerate them to a boosted regime where the lifetime in the lab frame is extended before they all decay away. And so there's substantial research and development which is needed in order to make this a reality. But the P5 report setting out the particle physics strategy in the US supports an R&D effort leading to, if feasible, a small-scale demonstrator, and then possibly resulting in a larger scale muon collider in the US with timelines and physics program complementary to the FCC program. And so it's conceivable that a muon collider could operate in this sort of intermediate period between the electron-positron collider at CERN and the hadron collider at CERN. Of course, any timeline that extends into the 2050s, 60s, 70s has significant uncertainties associated with it, and the R&D for this is very difficult. There are real problems that need to be solved, and it's not clear exactly if, how, and when that would be the case. But at least the R&D and feasibility assessment can begin and continue in the coming years. So to conclude, the LHC has already been an enormous success with the discovery of the Higgs boson and the measurement of its properties. There have been a wide range of beyond standard model searches, but alas, no discovery so far, but a competitive and ongoing precision measurement program which really far exceeds the initial expectations in many areas. The completion of the high luminosity LHC program will further extend the reach both of direct searches and measurements. And there is an ambitious proposal for a two-stage future circular collider program at CERN, providing on the one hand the most stringent tests of the standard model, but also a new discovery window at the energy frontier. And there is a complementary R&D program towards a possible muon collider in the US. So there's a rich and promising future for high energy physics with really quite detailed planning sketching out the program through the rest of this century at least. And that's where we stand at the moment. So thank you.
We have time for some questions, but speaking of which, What was Jeff Bezos running around, I heard? What's that all about? You don't have to say if it's.
Well, it was Katy Perry's birthday party,
Oh,
which for some reason was in Geneva, and they decided they wanted to visit CERN.
okay, that's good. If people want to visit, the rich and the famous want to visit CERN. Please, some questions. Mark.
So in the case where you're making, let me just call it the Z factory, the first upgrade. And it was a tremendous amount of B quarks that you mentioned. You also get a lot of neutrinos. Neutrinos get out, right? Is that an issue at all, or their interactions are so weak that they don't zap a farmer or anything when they?
Oh, so
this curve, so
yeah.
they get out.
Yeah, so that's not an issue for an electron-positron collider in terms of the final state particles. It actually is an issue in terms of a muon collider. Because in a muon collider, if you make it big enough and if you make it high enough energy, then of course, as the muons go around, some of them decay and you get a neutrino flux, and the neutrino interaction cross-section with matter does rise with energy. And so what happens is, and this is something which has been studied already in the context of a muon collider, where the effective dose at the surface does increase with the energy. And so if all of the problems of producing muon beams and cooling them and injecting them and accelerating them up to high energies are solved, then you can say, okay, well, now why don't we just build, a 30-kilometer ring, or maybe, reuse one of the existing ones and build a 200 TeV collider. One of the limiting factors would be the radiation dose at the surface induced by the high energy neutrino interactions. And people have looked at, various clever ideas like oscillating the plane of the beams in order to spread out the flux over a larger surface area at the intersection point with the Earth and things like this. But we should only be so lucky that these are the problems that we have to face, let's say.
Point didn't need to work. Thank you. So the present W mass uncertainty from theory is 16, as I remember. This really challenging comparison you showed. What would have to be done from the theoretical point of view to make theory competitive again?
So the interesting thing here is that what's called the theory uncertainty, you have to remember, is actually constructed by taking, the prediction is constructed by taking the experimental measurements of the other standard model parameters and then making a theoretical prediction. So the things that go in there are the mass of the Z, the weak mixing angle, the Higgs mass, and the top mass. And so the limiting factor in the theory, in what's called the theory uncertainty at the moment, is actually the top mass.
Yeah.
And that's the reason why, if you look closely, this plot actually says December 2063 at the top. And the reason it says December 2063 is that it's not enough to run the accelerator at the WW production threshold and collect, our hundreds of millions of Ws and make the measurement. You also need to run at the TT bar threshold, collect our millions of TT bar pairs and make the top mass measurement at the corresponding precision in order to match all of these things and get to the very ultimate precision for this comparison point between theory and experiment. Of course, there are many then legitimate, truly theoretical uncertainties that go in there in terms of the calculations, which need to be done at more loops, et cetera, that are also needed in order to be able to make the prediction. But these numbers are sort of making reasonable extrapolations, assuming that the precision of the calculations will improve, et cetera.
There's another dimension to this. I mean, you gave a fantastic answer, but what's happening from another point of view is you're indirectly probing larger and larger mass scales.
Correct.
So I don't know. There's been much interpretation along those lines, I don't think, but it's probably worthwhile to do so.
Correct.
Yeah, I think that's right.
There was a question.
Yeah, so I have maybe a naive question. Could you maybe explain for someone who's not a high energy physicist, when you measure masses, at like the GeV scales, how do you calibrate? Like, how does it?
You mean with precision?
With
precision of MEV?
and
Yeah.
accuracy?
Yeah.
How do you link that to
So-
like the SI
Yeah.
systems?
Yeah, so that is an excellent question. So what we do at the LHC is we always calibrate energy and momentum scales to so-called standard candles. And the two standard candles which are used are the Z boson mass and the J psi mass are the two that are most frequently used. Now, of course, those masses had to be measured at previous experiments. But in a circular electron-positron collider, there's something very clever that you can do, which is that you can polarize the beams. And if you have a polarized electron beam traveling in a circle, the polarization vector will rotate. And the rotation frequency is actually related to the energy of the beam, the radius of the accelerator, and a few other sort of physical details of the system. And so then what you do is you have the accelerator is instrumented with a large number of magnets. Some of them can be put in service as sort of polarization kickers. And so what you do is you scan through you have a rough estimate of the beam energy. And so you scan through the different frequencies that would correspond to the precession frequency of the spin vector. And then when you hit the resonance, the spin will flip. And it's called resonant depolarization. And so in that way, you can peg the beam energy to an RF frequency of the signal that's feeding these kicker magnets. And of course, as we've all learned, the most precisely measurable quantity in physics is a frequency. And that is where the relationship comes from. So the Z mass was measured at LEP with resonant depolarization. The J psi mass was measured at VEP in Russia, lower energy E plus E minus collider with a similar resonant depolarization technique. And this is what sets the ultimate mass scale. And then we use those to calibrate all of the other energy and momentum scales in the detectors.
And is it frequent in the community to maybe just remeasure these quantities, like with more precision, or is?
As often as we can, but it's hard. So in particular, to produce Z bosons in a circular E plus E minus collider requires one which is of order 27 kilometers. And there has only been one such collider so far. This, if we build it, will be the second one. And so we will do it again and much more precisely. It's actually an interesting historical anecdote that the limiting factor in the Z mass precision at LEP was the fact that this resonant depolarization trick, for various reasons related to the machine configuration, could only be done in separate runs from the ones in which the Z was actually produced and measured, which means that there is some extrapolation in time. And there's a lot of interesting details related to the phases of the moon pulling on the accelerator and suddenly changing its radius, and the ground return current from the high voltage on the TGV rails, which actually interfered with this.
Trains and more. Yeah.
Use DC current.
Last one, if we have one, yes.
So I've seen a similar plot to the Higgs coupling change measurements from the high luminosity LHC to the FCCEE for muon colliders. And to me, this plot doesn't look particularly optimistic, especially compared to similar plots I've seen. I think the Craig has one they did for a muon collider. So if the US physics effort is split between the FCCEE and a muon collider, where do you see the greatest pro from a physics case standpoint of measurements that you could get at FCCEE that you won't get at a muon collider?
So I think what I would say about this is that a muon collider, both in time scale and overall physics goals, is closer to being an FCCHH competitor than it is to being an FCCEE competitor, in the sense that it requires R&D, which is unknown in terms of length and breadth, whereas the E plus E minus collider can be built more or less today, modulo citing environmental assessments, funding, etc. And so in this sense, a muon collider, the appeal of a muon collider is actually rather that you can collide elementary particles at much higher energies, and you can have a sort of discovery machine with elementary particles in a much cleaner environment than the LHC. The fact that it can also do Higgs physics is of course good, but it's really on a longer time scale than what's foreseen for an E plus E minus Higgs factor.
And if I may make a comment here, the point is that we don't want to split out. We want to have staggering and projects between the US and here that they are appropriate in timelines, in scope, and cover gaps. And I think in that sense, this is why for the muon collider, we don't want to have it as a Higgs factory, but we want to go to the 10 TeV. And Josh showed the plot there that you can do probe precision measurements and probe for the 10 TeV scale. So there's multi-purpose machine up to the 10 TeV. Of course, you're not going to go to for the 100 TeV. You have to do the 100 TeV. But the idea is not split off, it's just continuation of the program. You take data from one, you build the next one, then, and you hold hands, that's the idea.
Yeah, I mean, I think what I would also say is that, this timeline extends, if you include also the operations, up to, 2090. But of course, if the CERN Council takes a decision in 2027 or 2028, that will be approving the funding and construction of the tunnel and of FCCEE. FCCHH is subject to further approval down the line, also once the R&D, which is needed for the high field magnets, is completed. And so, the final decision on that and the final shape of the next accelerator, after FCCEE is something that will come only later, even if, of course, it makes sense that there's this logical two-stage program. And, if we're going to invest in this big tunnel, we want to have already an idea of what the most likely scenario is for stage 2.
All right, let's thank Josh again.